Good morning, Michael.
Good morning, Matt.
We've been looking at derivatives, and let's look at some more applications.
Right, so we've talked about this before, the Taylor polynomial. So you have a function, and you want to compute an approximation to it, which is called the Taylor polynomial. And the key idea here, and I really want to stress this, the key idea is you pick a polynomial whose derivatives match the derivatives of the original function. That's all. Everything else is algebra.
Well, let's look at the algebra before we talk about the final result.
Okay, so Taylor polynomial, it's a polynomial. It could have degree up to, say, degree n.
So you're going to a0 plus a1x plus all the way up.
Let's do a few of them explicitly, and then we'll sort of worry about the last one at the end.
a3.
A3, and then dot, dot, dot. And it does end. It's a polynomial. It doesn't go forever. an x to the n. Now, to make our life easy, let's work at the point
0.
0. So what is p at 0?
P of 0 is equal to a0.
Because this is 0 plus 0 plus 0. This is just a0. If I compute the derivative at x, I have to look back a line. Can you tell me the derivative of this guy?
Yeah, so this is a constant, and the derivative of a1x is a1.
Okay.
And the derivative of this one is 2a2x, but we're evaluating at 0.
Let's not evaluate it. We're going to need this. We're going to need this later, so I'm going to write it down.
Oh, okay.
This is the derivative, and then here the derivative of the
Is 3a3 a sub 3x squared
and all the way up to the end.
n
X to the what power?
n minus 1.
Right.
Okay, let's do it again.
Let's evaluate at 0, because you were just
you're gonna
dying. You were dying
evaluate
to
it.
do it, weren't you?
I was just ready chomping at the bit. P prime.
B prime at 0. Thank you, Matt.
Okay, at 0, all these vanished, so we got a1.
A1.
So I've got a hunch that every time we do this, we're starting to pick off the coefficients. So let's do another derivative to check.
Okay, so let's do P double prime.
All right, so we now differentiate this. So constant 0, P double prime is 2a2 plus 2 comes down, 2 times 3 is 6.
I'm going to write it down as
2 times 3.
2 times 3, because
right.
there's a pattern happening
Yeah.
here.
And a3.
A3, and there's an x still, right?
Yep.
So this x squared becomes x.
And now bring down, differentiate x to the n minus 1 is n to the minus 1, and x to the n minus 2. Do we have to do another one?
Well, this was supposed to be at x.
Yeah. Oh, we have to evaluate
Now
it.
let's evaluate it at 0.
Okay, so 2a2
And all these other guys
disappear.
disappear.
Maybe we have to do one more for
You
the
know what?
pattern?
I think we're smart enough that we can see the pattern. See how we had a 1 in front of a0, 1, 2, 2. This is going to come out, and triple prime will be 3 times 2 times a3, right? Because
And then everything
else will be 0.
Right. Okay, so let's substitute back in.
Well,
let's solve for the a's, and then
let's do for the nth one. What happens if we go all the way to the n?
you'll eventually get to 1. So you'll get n times n minus 1 times n minus 2, and I think we call that n factorial.
So here we had a 3, here we had a 2, here we
Here you
have
have an n
so
plus,
this is the nth derivative.
is it going to be n or n?
Well, 3. So I think
Oh,
n
yeah, n.
factorial.
That's right.
an.
Oh, p.
At 0.
At 0.
That's just the pattern.
Oh, so we have the pattern here for any n, it's going to look like that.
Now, remember what we said about the Taylor polynomial. We want its derivatives to match the derivatives of f.
Right.
So here, this should match f at 0.
Right?
Here, this should match
F prime.
f prime at 0. Here, this should match double prime at 0, right?
And at the end,
And, well, here, we've got this one too.
F3, third derivative, now
And then this is the nth derivative.
at 0. Oh, so now we can see what an is, and what a3 is, and what a2
So
is.
tell me what an is in terms of f.
Well, we just divide by n factorial.
Divide by n factorial.
And that's at 0. So that's very cool. So now we could just use this for all the numbers less than n. And so we get the result.
So now we can write this polynomial. Can I squeeze it in here?
Yeah.
This will be f of 0 plus f of 1 times x plus,
Oh, wait, isn't there a prime?
oh, you're right, f prime at 0,
0. And now,
f double prime at 0, and divided by 2 factorial.
which is, yeah, 2 factorial. Plus
X squared plus
f triple
f
prime
triple prime
at 0. And that's x cubed over 3 factorial.
and all the way up to the nth derivative at 0 divided by n factorial, that's my an, multiplied by xn. Now, a lot of people teaching calculus just tell you to memorize this.
We don't have to memorize
You
it.
don't have to memorize it. We just say, make sure f and its derivatives match p and its derivatives.
And also, now we can go back to where we use this in real life.
Okay.
So if we neglect everything, a0 is just a constant. So the function is a constant near 0 in terms of its value. Now we pick off the slope
Right.
at 0.
That's the first derivative.
First derivative. The second derivative, we haven't talked much about the geometry of the second derivative. Would you like to give us a hint?
Well, very quickly, x squared is a parabola, so it introduces this idea of curvature to the function. So this gives you sort of the starting value. This gives you the slopiness. This gives you the curviness.
And I have to ask, you know what I'm going to ask, right? This one, x cubed. So
I learned it and I didn't believe it when I learned it. I'm going to see if you have the same word for it.
Well, the thing is this, is if we look just geometrically, we can see this is flat, this is a slope, this is a bowl. So you're looking at changes in the shape of a bowl. And you can imagine that you could have a downward bowl connecting to an upward bowl. And so when, let's draw it. And this point here, you've drawn it is often given a name, but it's where this curve is 0, and it's also flat there, but the bowl changes from an upward bowl to a downward bowl there.
So a change in concavity.
Yes.
Change in concavity.
So we have all these 4 geometrical progressions, which I think is wonderful. And again, in most textbooks, you don't see the geometrical connections.
Very good. Maybe, since we've been doing so many derivatives, if we took a function like sine, we know sine at 0 is 0. We know sine prime is cosine, so that's 1. Then you get zeros and ones with negative signs. And so a Taylor polynomial for sine of x is roughly the polynomial x minus x cubed
Over 3 factorial. Yeah.
plus x to the 5 over 5 factorial. And so on, up to some x to the 2n plus 1 over 2n plus 1. And you get a plus or minus here depending on
Where you are, odd or
where you are.
even.
And that's how you compute sine of x.
Good job.